In part one, we talked about the difference between arithmetic and logic. We also talked about how you use basically a lookup table, for example, when you're doing addition, that looks something like this, that you actually carry in your head. You probably learned this in first or second grade. You also learned how to do multiplication, once again in grammar school, and you have, I'm sure, memorized a table like this in your head, although you may not realize it. It's a lookup table. We'll see those a little later. We also developed some truth tables for binary arithmetic and binary logic. We said in binary arithmetic we have an addition table and a multiplication table. In binary logic we have an OR gate, or an OR operation. We also have an AND operation. We'll be talking about those a little bit more. Let's talk about binary arithmetic now. This is a table of binary numbers. You'll notice that at the top we have the numbers 1, 2, 4, and 8. These are called powers of 2. 2 to the 0 power is 1. 2 to the first power is 2. 2 to the second power is 4. 2 to the third power is 8. Down this side we have decimal numbers from 0 to 15. Now you may wonder why we call this decimal and this binary. Why isn't this decinary, or why isn't this binomal? Well, life is like that. It's just the way it is. Now I've shown here how you would write the equivalent or convert a binary or a decimal number to a binary number. I've written all the zeros in here, but I've eliminated the zeros in the rest of the table for a little bit better clarity. Every blank space is a 0. So if we want to write the number 1, well, that's easy. That's also a 1 here. If we want to write the number 2, that's also easy. That's a 2. 3, however, gets a little complicated, because to write a 3 in decimal in a binary system, we only have the numbers 0 and 1, so we have to write 1, 1. 2 plus 1 is 3. That's where we get this. Similarly, 4 is easy. 5 is 4 plus 1. 6 is 4 plus 2. 7 is 4 plus 2 plus 1, and so on, until we get down to 15. At 15, all of the numbers, all of the digits, the binary digits, are a 1. Here is the decimal operation of adding 5 and 3. We get 8. We know that. Here is 5 written in binary. That is a 4 and a 1, and 3 written in binary. So this is 5, this is 3, 2 and 1. We then look at our binary arithmetic table to add. 1 and 1, 1 and 1 is a 0 with a carry of 1. We write down the 0, we carry the 1. 1 and 1, 1 and 1, is a 0 with a carry of a 1. 1 and 1 is a 0 with a carry of a 1. 1 and 0 is 1. If we now look at our binary table, we see that 1, 0, 0, 0, 1, 0, 0, 0 is 8, which is the correct answer. Now let's look at how an AND operation differs from that. For an AND operation, we have to look at our logic tables. And in this case, we're going to be using this logic table. A 1 and a 1 is a 1. A 1 and a 0 is a 0. A 1 and a 0 is a 0. A 0 and a 0 is a 0. So the AND operation gave us 0, 0, 0, 1. As you see, those are quite different. And I emphasize this because in a second we're going to look at how you would actually build a circuit that could do an AND operation. Here's the circuit we're going to construct. It's a very simple switching circuit. By switching circuit, we mean it's a logic circuit made up of switches. This is switch number 1. We'll call that A. This is switch number 2. We'll call that B. This is an AND gate. It's an AND gate because to get a connection from this side to this side, switch 1 or A must be on and switch B must be on. Let me reemphasize that. A and B. The rest of the circuit is just an indicator. It's an LED, a resistor, and a battery. We'll worry about that later. Right now, just remember that this is only to show the circuit, whether the logic operation is true, the LED will be on, or is false, the LED will be off. I have rearranged the lighting and the camera angle so that you can see the switches of A and B, and at the same time, hopefully you'll be able to see the LED up here. I apologize that they're so far away I can't get them in the camera, but that's one of the downsides of using this unit. But later, as you'll see, the nice thing about this unit is we can go as far as programming a mini computer and doing all kinds of logic experiments on this same unit. So once you become familiar with it, you'll see that introducing it early like this was on purpose so that later we can use this for a lot of different logic experiments. Now here is A, here is B, and you notice the LED comes on. Now if I turn off B, the LED goes off. If I turn off A, the LED goes off. If I turn off A and B, the LED goes off. This is a very simple AND circuit. Now, we're using switches in this case, but one of the things that people realized early on when electronics began, they could use electronic devices like vacuum tubes in the early days, later transistors, and finally integrated circuits to do this kind of logic. So let's now look at a simple transistor switch. Here is how you might do that same circuit that we just showed with switches, only this time using transistors. The way this works is both of these transistors have to be on for there to be a connection from here to this ground. Now, if you're not familiar with transistors, don't worry about it. Just think of these as simple switches. In other words, if you apply the right signal here, this switch will turn on. If you apply the right signal here, this switch will turn on. If both switches are turned on, that is the equivalent of A and B. So once again, I hope you enjoyed this part, and you'll stay tuned for some of the future ones.